Okay, hello, welcome. So the goal of this video is to apply the Crank-Nicholson method that we used earlier. I was going to do it in the same environment so we could compare graphs, but I'll just tab over to it. I had a big error that I couldn't get past. So basically what we're going to do again is we're going to import numpy as np, and then we're going to say from plotly.subplots. We're going to import make subplots, and then we're going to use solve banded to solve the matrices that we used earlier. And so what we're going to do is, give me just a sec, I'm sorry. What we're going to say is that from linear algebra, SciPy, we are going to import solve banded. So we're going to shift enter that, make sure everything connects. Awesome. Okay, so we're going to set up everything just like we did initially the first time. So we need to set up our thermal diffusivity alpha, which is equal to 1 every time, every single time. And then next we're going to say how many increments that we want in our bar. And so let's say that we want 100 increments to be taken from the bar, and then we want to take, let's do 2,000 time increments. And then we want to set the size of each of those increments. So we can say that we want our X or our bar size increments to be in half increments, and that we want our time increments to be in half increments. And then we're going to say that we're going to set up our X values so that way we can plot them later. We're going to say that we want that to be NPA range of the number of increments that we have times the size of each of our increments. So if we have 100 increments times 1/2, 50 increments. And then from here, we need to incorporate our R back in. And so what we're going to say is, previously what we had was, actually I guess I can go over here because this doesn't work. So what we had that our R was our thermal diffusivity times the size of our increments, or our time, divided by, our size increment squared. And then when we did the Crank-Nicholson method, we got that our R was equal to alpha, or our thermal diffusivity, times our time increment divided by our size increment squared, and then we put 2 in the denominator for that. So from here, what we're going to do is we're going to set the uniform temperature across our bar and then redefine our first and last nodes or increments. And so we're going to say that our temperature is equal to full. We need to give the full shape, and that is the number of increments that we have, and we're going to set all of them to 20 degrees Celsius. And then for the first node, we need to say that our T0 is equal to 50 degrees Celsius, not bit length, sorry. And then our back indexed node, again, we could say 49, or I guess 99 now. Or we could just say -1 is equal to, sorry, I'm trying to keep spaces out. I think that might be what's giving me problems. So now what we're going to do is we're going to set up our our matrices. Let me get rid of this because this was for errors earlier, sorry. Our matrices. And so what we're going to do is we have our 3 main diagonals in our main matrix, and we're going to call our main matrix, I guess we'll just do A or AB. Doesn't matter, but we're going to have 3 main diagonals, and we're going to say our upper, main, and then lower diagonals. And so what we're going to do is we're going to say that, wrong one, sorry. We're going to say that our A diagonal from 0 to 1, this is also probably why I'm getting issues, is equal to -R for the Crank-Nicholson. And then we're going to say that our A matrix from 1, our main diagonal, because we're going to go upper, main, and then lower diagonal. And that's going to go from the beginning of our our matrix or of our array of temperatures all the way to the end is equal to 1 plus 2 point, we have to make sure we include that, times r. And then we're going to say that our lower is from our lower diagonal, sorry, is from the beginning all the way to our very end, our back indexed diagonal, or our back index node. Oh, right, I did it again. Oops. We need to define, I forgot our A matrix, and that all that is zeros from how many diagonals we want. We want 3 diagonals, and then we're going to say that it is our number of increments minus 2 because we have our first and last ones defined. Okay. And so now what we need to do is we need to set up our B matrix, and first let's make sure that this actually gives us values. Awesome. So now we need to set up our B matrix, and we'll call that, we could just do, I guess we'll just do lowercase b. But what we need to do is we need to say that that is equal to our 0, we're just going to set it all to 0 right now, of our number of increments minus 2. If we do that and we say, all right, give us B, we should get 0 all the way across. Awesome. And so the next step is to define the first and last nodes, which we've already put temperatures in. So we can say that our B node 0 is equal to, is equal to our temperature at 0 plus our R value times the regular temperature at our 0 node. If we do that, and then we say, okay, now show us B, we get a value for 50 there. And then if we do our B value at our back indexed node, we get that that is equal to, should be 80. The temperature at our back indexed node. Perfect. So now the only thing we have to do is graph this. This is where I got an error earlier. I hope I don't reach that error again. That would be very sad. What we need to do is we need to obviously say that our fig2 equals make subplots. And then we have to say that rows equals 1 and columns equals 1. Sorry, I forgot how to type. Let's make sure I'm still recording here. That would stink. Okay, good. Set that up. Awesome. And fig2, we need to add a scatter plot to this. We say that our x values, our x axis is dependent on the x variables which we set up, and our y values are dependent on our t values that we got set up. And then we need to say that the name of our graph is equal to, let's just do conditions. Awesome. So that works. So again, we have our node 0 at 50 degrees and then our node 49 and a half or 50 at 80 degrees. So I guess if I get rid of this, here comes the kicker. The next part is we have to incorporate the matrices again. So we're going to say that for I in range, we have our time increments plus 1. We need to say that our temperature from node 1 to our back index node is equal to our solve banded function, which requires where we want to go from, and then our two matrices that we're going to index. So we need A and B. Comma. Okay. Can't believe that worked that time. So then we're going to say that our B in this range is equal to our temperature. I actually forgot to put that in here. We need to say that our B is equal to our R value times the temperature from our second node all the way to the end plus 1 plus 2 times R, times our temperature from our first node index to our back index node plus our R value times our temperature from the very beginning all the way to our second back index node. Okay, and so what we're going to do is we're going to take this and put it down here. Make sure it agrees with that. Okay, so this is where the issue is. Overflow encountered in add. But I don't want long scalars, I want add. I want. What if we drop the size of these down? Okay. So something is happening here that is giving me a terrible error. I think I know why. I think I forgot how to do the problem. That's exactly what the issue was. Okay. All right, cool. So then from here, we just need to bring in our 0 node referenced earlier like we did. So we're going to say that our B node at 0 is equal or plus R times our T value, or temperature at our 0 node. Make sure that's okay. Yep. Yeah, okay. So if you learned how to do the problem right, you can do the problem. That's crazy how that works. It's equal to the B matrix at our back index node plus r times our temperature at our back indexed node, or reverse indexed node. Awesome. And so what we did it earlier. Now that I know, actually, shoot, I'll tell you what. If I do it up here, this one might work. Okay, disregard that, I guess. The last thing we want to do, like we did initially in the very first video, was have the graph return to us only whole numbers at our time increments. We don't need to worry about the other things, so we can say that if I modulo equal 100 equals 0, then we can say, okay, give us just the graph, and we can say that x equals x, y equals our temperature values, and then we can say that our name is equal to I times, what was it, our size increments. And then why are you only showing up with one graph? Let's try a new value for our delta t, so long as it's less than 1. Let's do 0.8. How about that? Oh yeah, see? That was the main point of the Crank-Nicholson, was to derive or be able to show that so long as our t value is less than 1, that we get a value. Because if we had our delta t set to, let's try 1.2, I feel like it should break. If it does, yes, good, squiggly. But as soon as I go to, let's try 0.99999. So we start to get wigglies the closer and closer we get to 1. But as soon as I drop it to 0.90, we get graph values. Thanks to the Crank-Nicholson equation.